Good. So now at least we have this example, first practical implementation of universal hashing here. But actually we ignored a few details here that will motivate the next thing. So let's say you actually want to code this you will in your projects. It looks kind of easy to implement this, but actually it's not so trivial. Let's have a look at what happens if you wanted to implement this, in particular, if you want to hash, say, 64-bit integers, then you actually get into trouble. So let's try to be a little practical, and then we'll see. This also motivates the next hash function we'll see. It's much more practical, but maybe a little bit trickier to analyze. So let's say I wanted to implement this for u being, I guess we're looking at the integers from 0 to 2 to the 64 minus 1. These are the ones we want to hash. So our x lies in this range, which means our prime p has to be at least 64, so it's some number bigger than 64. So it doesn't even fit in a normal 64-bit integer if you wanted to implement it, right? So p here, these 2 to the 64. 2 to the 64 is not itself a prime, so it has to be strictly larger than 2 to the 64. You need more than 64 bits to store your number. The element you're hashing can be anything less than equal to 2 to the 64 minus 1. In particular, the product can have more than 128 bits. It's quite annoying, right? If you don't have you don't even have a 128-bit type in most programming languages. So this can even be larger. So even just computing this a times x, if you wanted to implement it exactly, you cannot just do overflows in your programming language. You need to actually compute this explicitly if you wanted to do it exactly as it's stated here. So how could you implement this? I think one way to look at it is, how can I even compute a times x? That's maybe the first step. And what you could do here is basically do the primary school long multiplication method. So how would that go? So I guess your a, right, that needs to have more than 64 bits. Maybe we can think of it as consisting of maybe some 3 chunks of 32 bits. Could find a prime that is small enough that you can at least partition it into chunks of 32 bits. Your x fits in 64 bits. The interesting thing is, if I have a 64-bit multiplication on my computer, I can multiply two 32-bit numbers without getting an overflow, right? I cannot even multiply two 64-bit numbers without getting an overflow. So what I can do is I could think of my two numbers as all these chunks of 32 bits, and then I can do the primary school method here where you have kind of doing long multiplication. So what you're doing is you're going over these pairs, you're going to multiply these two in 64-bit precision. And then you're going to kind of add it down here with no shift. Then you're going to do these two, and you're going to insert a shift of 2 to 32. So you're kind of going to multiply these and shift them to this position and add them up. You're going to multiply these, shift them 2 positions, add them up. You're going to multiply these, and these. So you actually need 6 64-bit multiplications. And then you need to do a bunch of additions and handle various overflows manually. These not here. That's already a little tedious. And now what gets even worse is now you have this number. Each of these are 32 chunks, so this is like 64 bits, this is 128 bits. This is even more, right? So you have a lot of bits in these numbers. You need to do modulo of prime. There's no standard. There's no operation on your CPU for doing modulo of prime that's this big. So how can you even do this mod operation on this number here? Right? It's already that's a problem too. I'm going to show you one way of handling it here. That actually can also sometimes be used for hashing smaller numbers. It can be more efficient than using the built-in modulo operation on one. So there's a trick that allows you to actually do this mod on this big number here. And this trick is basically saying, let's look at a particular choice of prime. So there's some primes that are this particular structure. They're called Mersenne primes. Now, Mersenne primes. So a prime P is a Mersenne prime if P is equal to 2 to the Q minus 1. So it's 1 less than a power of 2. These are called Mersenne primes. And it's been shown that there are infinitely many Mersenne primes. And I prepared 2 for you. And let me just check because to make sure I write, yes. 2 to the 89 minus 1, 2 to the 61 minus 1 are 2 examples. 89 minus 1 is a prime, and 2 to the 61 minus 1 is a prime. Okay, so it's not all numbers in this form that are prime, but there are infinitely many such, and these are 2 examples. Why are these useful? So let's try and use those for hashing up here. So, okay, this one is too small, right? Because we need our prime to be at least 2 to the 64, but we could actually use the prime 2 to the 89. So, what is special about using a Mersenne prime? How does it help us if we want to implement this? So, I have some number and then I want to do mod p on this number. Let's call it y to not confuse it. So I want to compute y mod p. Now let me rewrite y. So I can write y also as well. How many times? How many times does 2 to the q divide y times 2 to the q? So this is kind of saying I do an integer division by 2 to the q, and I kind of look at so integer division 2 to the q multiplied back up to 2 to the q. So this is the largest number less than y that is 2 to the q divides. Right? And then I have a remainder which is exactly equal to y mod. I can write any number like this. Right? So if I just take the mod 2 to the q, to note 2 to the q is the power of 2, it's not the prime. And I also can write, and then I have the integer part over here. Now, let's imagine I want to do y mod p. These nice rules, and if I do modulo on a sum, it's okay to do modulo individually on the terms. And then I can still do a modulo at the end. And I can also do it on the individual factors in the product. So what I'm going to do now is I'm going to notice 2 to the q is easy in modulo p. Right? Because what is the remainder if I have 2 to the q and I divide by, if I do 2 to the q minus 1, what is the remainder here? Yeah, 1. It's 1, right? Because 2 to the q is just 1 larger. So this is 1. So if I want to do this modulo p, it's the same. So y mod p is also, so how do we write it? Right, it's congruent to I over 2 to the q plus y mod. Makes sense? So I can kind of get rid of this factor. Okay, why is this useful? Let's have a look at why is this useful. So first of all, let's maybe take this one first. Y modulo 2 to the q. I'm looking at binary numbers. What does this correspond to? Binary representation of y. Y modulo power of 2. No, yeah.
Corresponds to redshift and left shift.
I think you're confusing it with a division. I think, yeah. So this just corresponds to, maybe let's call this y instead. Yeah, so almost. If I do modulo 2 to the q, let's say I have q bits, then it corresponds to, so I just set everything above 0, and I keep these down here. Right? So that's the modulo 2 to the q. So this is easy. Even if I have these many bits, I can actually, with standard operations, set some of them to 0. It's kind of easy. So I can actually compute this part here. It's easy enough to do. And then this one is basically what you said. Y integer division by a power of 2 is shifting the bits by q positions. So that is basically take everything here and shift it down here. So that I can actually also implement manually pretty easily. Okay. And now, what do I have? How big is this number now that I need to do mod p on? Let's try to have a look at this concrete example here. So, right, how big was y, the thing that we're hashing? So the thing that we're hashing, it would correspond to this a times x that we're looking at. This is what we need to do in the hash function at a times x. Let's ignore the plus b for now. I want to do a times x. How big is a times x? Well, x is it's less than 2 to the 64. A is less than 2 to the 89. Product is, I guess, less than 2 to the 89 plus. That's how big this number is. That's the thing that I'm now doing integer division by 2 to the 89. So the number I have left is less than 2 to the 64. This number here is less than 2 to the 64. That's nice. So it's also less than p. Okay. And then there's the other one here, y mod 2 to the q. Well, this is of course less than 2 to the q, just because how mod works, right? So this is less than 2 to the 89 minus, just less than 2 to the 89. So I have a number that's less than 2 to the 64 plus a number that's less than 2 to the 89. Then I get a number that's less than equal to 2 to the 64 minus 1 plus 2 to the 89 minus 1. That is definitely less than equal to 2 times 2 to the 89 minus 2. And this is 2 to the 90. So, and that is less than 2p. Makes sense? Less than 2p. And so I think maybe you can even do a little bit tighter here. But now, so we have a number here that is, I guess it's at most this large. Part here, maybe this is the easier part to look at. And then we're adding a number over here that we argued was at less than 2 to the 64. We add another number that's at more 2 to the 64. So all these numbers that I need to do mod 89 minus 1 on, the sum of them, I guess you can even show is less than 2p. Does that make sense? That I'm adding a number that's less than 2 to the 64 with a number that's less than 2 to the 64 with a number that's less than 2 to the 89. The sum here is less than 2 times 2 to the 89. Which means what I can do now is I can just do a very simple modular operation. I add the two up, I add these two numbers. Then I do a check manually. If the sum, let's call it S, if S is larger, greater than equal to P, then I just set S to S minus P. That's another way of doing mod P, right? A simple way of doing mod P. And I only do it once because then I know I'm less than P, and then my mod is correct. So basically what I can do is I can compute these two numbers with shifts and masking. I can add them up. And in addition, I can do a comparison to P and do a subtraction if I want to. So then I can actually do all this stuff on these long numbers using standard operations. So it can be implemented, but I think you will agree that it doesn't look that efficient actually if you want to implement. There's still these 64-bit multiplications. There's all these shifts and stuff like this. So it's implementable in constant time. It's maybe not that practical. So what we're going to see now is another hash function that is, I guess, significantly